Hello everybody, welcome into another lesson. So today we are going to solve systems of equations in three variables. Now the idea of this is to figure out where three lines or three planes intersect in space. So you have x plus y plus z equals 6, 2x minus y plus z equals 3, and then 3x minus z equals 0. Well, largely with three variables, you rely heavily on elimination. And then you can use substitution after the fact, but here's the thing. Your goal is still, with elimination, to try to eliminate one of the variables. I think if we look at the first two equations, we can definitely eliminate y, because in the first equation, your y is positive 1, your second equation, y is negative 1 for the coefficient. So, if we just add the first two equations together, you'll get x plus y plus z equals 6, and then you'll have 2x minus y plus z equals 3. So let's just go ahead, add these two equations together. You'll get 3x for the x, the y's are gone, then you'll just have plus 2z equals 9. So out of these first two equations, we got 3x plus 2z equals 9. Now what we can do is we can take the combination of these first two equations, the 3x plus 2z equals 9, and add it to 3x minus z equals 0. Alright, well, we have two choices. We can either try to eliminate x next, or we could try to eliminate z. Well, we have the same coefficient on x, so why don't we just go ahead and subtract the second equation from the first? That'll make life a lot easier. 3x minus 3x is 0, 2z minus negative z, that turns into 3z equals 9. And then you solve for z, you get that z equals 3. So we found z to equal 3. Now, what you can do, we see we have 3x minus z in the original equations. If I put in that z value of 3 into this third equation, I can solve for x. So 3x minus 3 equals 0, which would give me that 3x equals 3, which would give me that x equals 1. So I found x and z. Now I just got to take these values, plug these into one of these equations, and solve for y. I think we'll definitely go with the top one. So I could put in my 1 for x plus y plus that 3 for z, which would equal 6. That's just going to give me y equals 2. So now I found all three x, y, and z values. I get what's called the ordered triple, 1, 2, and 3, where these three lines intersect in space. They intersect at the ordered triple 1, 2, and 3. The ordered triple 1, 2, 3, your x, y, and z coordinate of where these lines intersect. So largely you kind of solve these the same way as the two variable systems, only you got a little bit more work to do. And I got more of these. Alright, let's see. We have x plus y plus z equals 2. Negative x plus 3y plus 2z is equal to 8. And then 4x plus y equals 4. Okay. So you got x plus y plus z equals 2, negative x plus 3y plus 2z equals 8, 4x plus y equals 4. Alright, so here's the thing. In the third equation, you don't have a z variable. You technically do, it's just the coefficient on z is 0. So what you got to do then, I'm going to suggest, is we try to take the first two equations and eliminate the z variable, so then we can get a combination of the first two equations and add it to the third, and then eliminate one of the other variables. So let's deal with these first two equations here. You're going to end up with, let's just look at x plus y plus z equals 2, and then negative x plus 3y plus 2z equals 8. Just look at these first two. If we want to eliminate z, we can multiply the top equation by negative 2 and then just add the first equation to the second. So let's go ahead and multiply the top equation by negative 2. You would get negative 2x minus 2y minus 2z equals negative 4. And then you still have negative x plus 3y plus 2z equals 8. Now all of a sudden we can eliminate the z's if we go ahead and add these two equations together. You should get negative 3x plus y. The z's are gone. That would give you 4. So you get negative 3x plus y equals 4. Now out of the combination of these first two equations being manipulated, we can add that to the third equation and eliminate one of the other variables. So you're going to have negative 3x plus y equals 4. Then you're going to have 4x plus y equals 4. Alright, well, you have a positive 1 coefficient on y in both of these equations. Why don't we go ahead and subtract the second equation from the first? That way we can eliminate y. So negative 3 minus 4, that would give you negative 7x. Y minus y is 0. 4 minus 4 is 0. So you got negative 7x equals 0. That's just going to give you x equals 0. Alright, so we found the value for x. Now what about y? Why don't we take that x equals 0, substitute that into the third equation of the original, so you would have 4 times 0 plus y equals 4. That would give you y plus 0 equals 4, or simply y equals 4. Alright, so now we have found both x and y. Just take those values, substitute them into one of these equations, and solve for z. I'm going to vote for the top one. So x is 0, plus our y value of 4, plus z equals 2. Well, you would just get z equals negative 2. So now we found x, y, and z. So the ordered triple where these three lines in space intersect is going to be at 0, 4, negative 2. So these three lines would intersect at the order triple 0, 4, and negative 2. Alright. Now, let's change it up a bit. So we have 4x plus y minus 3z equals 11. We have 2x minus 3y plus 2z equals 9, and then we have x plus y plus z equals -3. Okay, so we have all three variables present. So we have 4x plus y minus 3z equals 11, 2x minus 3y plus z equals 9, and then we have x plus y plus z equals -3. Well, we still need to pick a variable to eliminate. It really doesn't matter where we go, honestly. It honestly doesn't matter. I'm going to vote we go for y. I'll tell you why we go for y. Because if you look at the first and third equations, you have a single coefficient of +1 on both of those. And then you just have a -3y in the second equation. So I think y is going to be our best to eliminate. Okay, so how are we going to do that? So here's what you got to do. We're going to take 3 times the first equation. So let me write out the first equation again. 4x plus y minus 3z equals 11, okay? And then we have 2x minus 3y plus 2z equals 9. Well, if I go for eliminating y, I need to multiply that top equation by 3, and then I can just add the two equations. So let's go ahead and do that. So this would give me 12x plus 3y minus 9z equals 33, and then I can just leave the second equation alone. That would give me 2x minus 3y plus 2z equals 9. Now I can simply add these two equations. 12x plus 2x, that's 14x. 3y minus 3y is 0. Negative 9z plus 2z, that's minus 7z. Then 33 plus 9 is 42. So there's one equation with y eliminated. Now, let's also look at the first and third equation. We can produce yet another equation where we eliminate y. So if I take 4x plus y minus 3z equals 11, and then I have x plus y plus z is equal to -3. Look at my coefficients on the y. They're both +1, so all I need to do is subtract the second equation from the first. I can eliminate y. So 4x minus x, that's 3x. Y minus y is 0. -3z minus z, that's -4z. 11 minus -3, that equals +14. So now I have two equations I've produced where I've eliminated y. I get 3x minus 4z equals 14. So with these two new equations with y eliminated, we now need to add these together. So you'll have 14x minus 7z equals 42. And then you'll have 3x minus 4z equals 14. Well, we need to pick another variable to eliminate. I'm going to vote we eliminate z. So if I multiply the top equation by -4 and multiply the second equation by 7, I should be able to cancel out z. So let's show you what that's going to look like here. Top equation by -4, so what's -14 times -4? That's going to be -56x plus 28z is equal to, now what the heck is 42 times negative 4? I have an idea, but I want to get it right. I want to say it's negative 168, but let me be sure on that. I'm right. It's negative 168. And then we're going to take 7 times the bottom equation, so that would give you 21x minus 28z equals, what's 14 times 7? We need to figure that out. That's 98. Alright, so now you notice I can add the first and second equation together. I could completely eliminate z. So let's do that. So negative 56x plus 21x, that's going to be negative 35x. 28z minus 28z is 0. Negative 168 plus 98 is 70. Now I have negative 35x equals 70, which would just give me x equals negative 2. So I ended up finding x to be negative 2. Now, since we've eliminated y, we base this x value off of two equations where we eliminated y. We need to pick one of these two equations with the y variable eliminated and stick the x value into that and solve for z. That would be the next thing we do. I'm going to pick the 3x minus 4z equals 14. So if I take 3 times negative 2 minus 4z equals 14, I'll end up getting negative 6 minus 4z equals 14, which would give me negative 4z equals 20, and then simply put z would equal negative 5. So now I have found x, I've found z. All I have to do now is solve for y. I put both my x and z values into one of these three original equations and I can solve for y. Let's go for the bottom one since it looks like the easiest. So x was negative 2 plus y, which we don't know yet. Z was negative 5. Then the right hand side equaled negative 3. So y minus 7 equals negative 3. That means y is going to end up equaling 4. Now I found all three values, so these three lines intersect at the order triple negative 2, 4, and negative 5. So at the order triple, negative 2, 4, and negative 5, these three lines intersect. All right, let's see. We have negative x plus 3y plus z equals 4. Four x minus 2y minus 5z equals negative 7. Okay. And then 2x plus 4y minus 3z equals 12. Alright, so here's another system with three variables. We have negative x plus 3y plus z equals 4. 4x minus 2y minus 5z equals negative 7, and 2x plus 4y minus 3z equals 12. Well, again, the goal is to start by eliminating one of the variables. If we're really looking at this here, I think y is going to be the most trickiest because of the coefficients. So we can either go for x or z. Or you can go for any of them. It's just you're going to do more work if you go for y. But I'm going to go for x personally. So let's go for two equations where we've eliminated the x variable. So if we take the first and second together, so let me write out the first and second equations again. Negative x plus 3y plus z is equal to 4. And then we got 4x minus 2y minus 5z equals negative 7. We want to eliminate x, we've stated. So if we multiply the first equation by 4 and then add these together, we can eliminate x. So let me multiply that first equation by 4 first. You'll get negative 4x plus 12y plus 4z is equal to 16. Then you have 4x minus 2y minus 5z equals negative 7. Now we can add these together and we can eliminate x. So negative 4x plus 4x is 0. 12y minus 2y is 10y. 4z minus 5z, that's just minus z, equals 16 minus 7, which is 9. So you have 10y minus z equals 9. There's your first equation with x eliminated. We need to repeat the process, though, to find a different equation. If you look at the first and third, you could just multiply the first equation by 2 and then add them together. So let me write out these equations again. Negative x plus 3y plus z equals 4. And then let's write the third equation below it. You have 2x plus 4y minus 3z equals 12. Well, let's multiply that top equation by 2. You get negative 2x plus 6y plus 2z equals 8. And then you'll have 2x plus 4y minus 3z is equal to 12. Now we can easily add these two equations. We can once again eliminate x. So negative 2x plus 2x is 0. 6y plus 4y is 10y. 2z minus 3z, that's minus z. And then 8 minus 12, that's negative 4. We have just now found two equations where x has been eliminated. So now we can just take these two new equations and put them together. So you have 10y minus z equals 9. You also have 10y minus z equals negative 4. So let's go ahead and subtract the second equation from the first. We can actually eliminate y. 10y minus 10y is 0. Negative z minus negative z actually is also 0. And then 9 minus negative 4 is 13. Well, you got a false statement. You have a false statement. 0 does not equal 13. That means you have an inconsistent system. So you have an inconsistent system which means there's no solution. Now, here's the thing though, because we have 3 lines, right? This no solution means there's no solution to where all 3 of them come together. It doesn't mean that 2 of them couldn't come together at some point. It's entirely possible, but all 3 of them don't, and that means at least 2 of the lines are parallel to each other. It's possible they all 3 are, but at least 2 of the lines are parallel. But this means that all 3 of these do not come together whatsoever in one spot. So there is no, that's what geometrically that means. So there is no solution. Alright. Let's do another one of these, then I'll show you some shortcuts. Well, I don't really mean shortcuts, but there's a trick we can tell you about. Alright, x plus 2y plus z equals 1. X minus 2y plus 3z equals negative 3. 2x plus y plus z equals negative 1. Okay, so another system of three equations. X plus 2y plus z equals 1. X minus 2y plus 3z equals negative 3. 2x plus y plus z equals negative 1. Well, we got choices for variables we can eliminate. And they're all three pretty fair, I gotta say. They're all very small coefficients. It really wouldn't matter. I'm going to tell you why I'm going to go for y, though. Because in the first and second equation, you have the same coefficients. The only difference is one's positive, one's negative. Wouldn't it make sense, then, if we try to eliminate y first? So let me write out the first and second equations again. So x plus 2y plus z equals 1. X minus 2y plus 3z equals negative 3. Now it's pretty simple. We can just add the first and second equations and eliminate the y variable. So this would turn into 2x plus 4z equals negative 2. So there's your first new equation with the y variable eliminated. Now, why don't we look at the second and the third? Because we want to eliminate y, but you have a negative coefficient and a positive coefficient. If I just multiply the third equation by 2 and add the second and third equation together, I can also eliminate the y variable. So let's write out the second and third equations here. So x minus 2y plus 3z equals negative 3. And then 2x plus y plus z equals negative 1. Why don't I go ahead and multiply that second equation by 2? So I'll have x minus 2y plus 3z equals negative 3. 4x plus 2y plus 2z equals negative 2. Now I can just add the first and second equations, and I can also eliminate y. So this would turn into 5x plus 5z is equal to negative 5. So now I have two equations where I've gone ahead and eliminated the y variable. So let's bring those two equations together. You'll have 2x plus 4z equals negative 2. Then you're going to have 5x plus 5z equals negative 5. Alright, it doesn't really matter which variable we seek to eliminate. Personally, I'm going to recommend we go for x because x has a smaller coefficient in the first equation. So let's go ahead and multiply the first equation by 5. You'll get 10x plus 20z equals negative 10. Then multiply the second equation by 2. You would also get 10x there plus 10z equals negative 10. Now let's go ahead and subtract the second equation from the first. You can eliminate the x variable that way. So you would get 10z equals negative 10 minus negative 10. That would just be 0. 10z equals 0, so z equals 0. Alright, so we found the value of z. Now what about, next we need to find x. So we're going to stick that into one of these two equations where we have eliminated the y variable. I'm going to go with the top one. So we'll take 2x plus 0, because 4 times 0 is 0, equals negative 2. That means x would just have to equal negative 1. So now we found z to be 0, we found x to be negative 1. Now we just have to stick these into one of these three equations and solve for y. Personally, I'm going to vote for, why don't we actually go for the third one? I kind of like the looks of that because we can get more of a direct answer for y since it's positive 1. So we'll have 2 times negative 1 plus y plus z, which is 0, is equal to negative 1. So you'll just get y minus 2 equals negative 1, which would give you y equals 1. So now we found the ordered triple where these three lines intersect at negative 1, 1, 0. So these three lines will come together at negative 1, 1, and 0. Alright, so those were solving some basic systems. Now, what if we run into a situation where you have more equations than variables? What happens in that situation? So let's say you have something like x plus y plus z equals 1, x minus 2y minus 3z equals 5, 2x minus 3y plus 4z equals 7, and then you have negative 5x minus 7y minus 6z equals 11. So in each of these equations, you only have 3 variables, but you have 4 equations. You have more equations in the system than you do variables. If that ever happens, there's no solution. You don't have to bother with elimination. You don't even have to bother with that. There's going to be no solution. If you ever have more equations than you have variables, there's no solution. So that's going to save you a lot of grief right there. Now, what if, on the other hand, we have less equations than variables? Which I have some good examples of that here. So, for example, we have x minus 2y plus 5z is equal to 2. And then you just have 4x minus z equals 0. So you have a system of equations with 3 variables but only 2 equations. So you're going to go from no solutions to infinitely many solutions. If you have less equations than you do variables, there's going to be infinitely many solutions. But I want to show you how the book is going to list it in your answer key. There are infinite solutions, but your book isn't just going to say that. There's a way it's denoted, and if you go to your answer pages in the back of your textbook, you're going to see it listed differently. So the goal is going to be here, let's solve for z. We can just say z equals 4x, right? Okay. Well, why don't we call, it's just going to be 4 times whatever x is. Why don't we call x a? We'll let x equal a, so that means z is going to equal 4 times a. where a is just some real number. That's all that means. A is some real number. And this is only used when you have infinite solutions. So now take your values for x and z, put that in the original equation, you can solve for y. So you'll have a minus 2y plus 5 times 4a equals 2, which would give you negative 2y plus a plus 20a equals 2. You get negative 2y equals 2 minus 21a. So that would give you y would equal 21 halves a minus 1. So it's going to be y is going to be 21 halves times some real number minus 1. So you're going to see the answer listed in your book something like this, as a 21 halves a minus 1 and then 4a. That's how you would see the solutions listed in your book. So if you ever see that notation, that means you have infinitely many solutions where a is some real number. And again, just like in systems of two equations with two variables, infinite solutions means they're all the same line. That's all that means. So let's do some more. Let's do another example of this. I think we need at least one more. Let's pick a harder one though. So we have 10x minus 3y plus 2z equals 0. And then we have 19x minus 5y minus z equals 0. Okay, so again, you have only two equations, but you have three variables. Right off the rip, we know there's infinite solutions. We can establish that. There are infinite solutions. However, again, your answer key in the back of your textbook is not just going to say infinite solutions. We're going to want to temporarily eliminate one of these variables. So I think it's safe to say z is our best bet. Let's multiply the second equation by 2, and we can eliminate z. So let's take 10x minus 3y plus 2z equals 0. Multiply the second equation by 2, you'll have 38x minus 10y minus 2z equals 0. Now you can add these and eliminate z temporarily. Well, you're going to end up with 48x minus 13y equals 0. So you see how nasty this can turn very quickly. Personally, I'm going to vote we solve for x. So this is going to then be 48x equals 13y, where then x would equal 13/48 times y, which unfortunately 13/48 just doesn't reduce. Since we found x, why don't we define y as the real number a? So y would equal a. We'll make y that a, which would have to then mean that x would equal 13/48 times that a. So now all we need to do is solve for z in terms of a. We'll put that into the bottom equation since the coefficient on z is -1. So we're going to take 19 times that 13/48a minus 5a minus z, set all that equal to 0. Now, this is where it's going to get fun. Let's do, what is 19 times 13? That's 247. 247 over 48a minus, okay, so what is 5 in terms of 48? 5 times 48, that's 240, minus 240 over 48. We can move that z over to the right-hand side. So now all you have is that z would equal 7/48 times a. So you'll see your solution listed something like this in the back of your book. It would be 13/48 a, 7/48 a, for an ordered triple where there's infinite solutions, and it's just that a is just some arbitrary real number. So that's the case for infinite solutions, and again, that would mean that these are actually the same line. That's what that would mean. So that's it for this lesson. Next lesson, we're going to get into one of my all-time favorite topics, which is partial fraction decomposition. And it does involve the use of systems of equations, but it's very important because partial fraction decomposition comes up in calculus very heavily. Very heavily. So I hope everybody has a great day. Take care.